So this is all going to be about AS atomic structure, which is kind of atomic structure and chemical bonding, which is kind of which would be very different from what you studied in O levels about atoms and molecules. So AS atomic structure. Now we will start with the very basics. The first basic thing is when you talk about atomic structure, that's that what is present in an atom. Now, an atom is made up of three things, and those three things are protons, neutrons, and electrons. So you need to know. So this is very basic. It's you've already studied this in O levels. So you've got a proton, you've got a neutron, and you've got an electron. The first thing is the relative mass. The relative mass of a proton is 1, of a neutron is also 1, and of an electron, that's 1 over 1836. And then you have the relative charge. The relative charge of a proton, neutron, electron. Proton is +1, neutron is no charge, and electron is -1. So this is very basic. And remember, this is relative charge. That's it, and this is not the actual mass. It's a mass when you talk about mass in comparison to each other. So proton having a mass of 1 means that a neutron having a mass of 1 is that they both have equal masses. The electron is 1836 times lighter than the proton and the neutron. So this is not the actual mass. What it just tells you is that they both have the same mass. And similarly, +1 and -1, that's not the actual charge. It just tells you that they have the exact same charge, except that the sign is different. +1 means the actual charge is plus 1.6 times 10 to the power -19 coulombs. -1 means that it has exactly the same charge, except that it's now a negative charge, which is -1.6 times 10 to the power -19 coulombs. But that is used mostly in physics. We're going to just stick with +1 and -1. So whatever the charge on a proton, the charge on an electron is going to be exactly the opposite, and the neutron will have no charge whatsoever. Again, you must know that positive, or simply unlike charges, they attract, or opposite charges attract. While at the same time, the same type of charges or like charges, they repel. So you have a question where you get a question where you have two plates. So there's plate number 1, that's plate number 2. One of the plates is connected to the positive terminal, the other one is connected to the negative terminal. So let's say the top one is the positive one, and the bottom one is your negatively charged plate. And there's a beam of electrons, that's a beam of particles that is going through the. Just a second. So there's a beam of particles, and that beam of particles is traveling through this through these two plates. Now we obviously know that the electrons are going to get attracted to the. So the electrons are going to get attracted towards the positive plate. So that's where the negative electrons are going to go. The protons would get attracted to the negative plate, and the neutron is going to stay right in the middle. It's not going to get attracted to either plate. The electron is going to have more deflection. So it's going to have more deflection, and also remember that this deflection, it depends on two things. The deflection is proportional to the charge and inversely proportional to the mass. What that kind of indicates is that when you have if you have greater charge, there's going to be more deflection. It's obviously there's going to be more attraction. Like if something has +2 charge, then it's going to get attracted more. If something has -5 charge, it's going to get attracted to the positive plate even more, and it's inversely proportional to mass, which means that that heavier particles, they get deflected lesser, and lighter particles get deflected more. Is this clear?
Yes, sir.
France, Lisha, Anna, is this clear? Aisha, Mayim,
Yes,
clear?
sir.
Acha,
Yes,
Yes.
sir.
that's okay. So that's all basics. Just but do remember this thing. Specifically, just a second. Specifically this thing about deflection, because I do remember there was. I mean, we're going to do some questions on this later on, but there was a question where you had uh, particles which were made up of protons. I mean, all particles are made up of protons and electrons. I mean, any atom or ion, that's a bunch of protons and electrons grouped together. So there was this question where they were talking about relative comparison. So there was hydrogen, and there was which had only one proton. Anyways, we're going to do that question when we start doing past papers for this. Okay, so we'll keep that for later. But do remember this thing, that deflection is inversely proportional to mass and directly proportional to charge. The next thing that we're going to do is we've studied proton, neutrons, electrons. The very next thing that we're going to do or cover is uh, the structure of an atom, which you already know from O levels. But I'm just going to brief you shortly, or just give you. I mean, the A level structure of an atom is quite different. So, what is the structure of an atom? The structure of an atom is that you have your. So, the structure of an atom is that you have a nucleus, usually, and I mean, it's always, an atom always has a nucleus. And the nucleus has protons and neutrons. That's present in the nucleus. And then you've got your electrons that are uh, revolving around, and they are in shells. So that, let's say that's shell number one, and I've got, let's say, another shell. So the electrons are all present in shells around the nucleus. So you have electrons, and why are the electrons attracted? So electrons are in shells. So that's your electrons in shells. That's a positive nucleus. And that nucleus contains nucleons, which are protons and neutrons. Like, a proton is a nucleon, and a neutron is a nucleon is anything that is in the nucleus. So this is obviously, the center is obviously positively charged, because you've got protons in it, and neutrons have no charge, and the electrons are attracted to it. So the electrons in shells are attracted to positive nucleus, and there is a force of attraction. Like, all of them, all these electrons, etc., are attracted to the nucleus, and that force is known as, in chemistry, you always have one force, which is an electrostatic force of attraction. That's the force of attraction between oppositely charged particles. So all the electrons, so this is the center, is the positive nucleus. That's a very well defined center, and all these bunch of electrons are getting attracted to this positive nucleus. ठीक है, is this clear? ठीक है, very basic. Clear है सारों को?
Yes, sir.
Okay. Now that's what an atom is. And you studied a lot of things about atoms, right? Uh, you studied about the 288 electronic configuration. You've studied that you've got lots of shells around an atom. So there's shell 1, there is shell number 2, and all these shells are full of electrons, depending how big the atom is. Like most atoms, they don't have shell number 4, but you can go up to shell 5 or shell 6 as well. So it just keeps going on. Does anyone know how many electrons maximum can be accommodated in shell number 1?
2.
Okay, that's 2.
2.
Acha, what about 2? The second shell. How many electrons does that
8.
have? That's the third one. I mean, O levels use it. As the third one has a total of a maximum of 18 electrons. The fourth one has a maximum of 32 electrons. The fifth one has a maximum of 50 electrons. There's a formula which is 2n squared. You can use that where n is the shell number. So as you move further away from the nucleus, and I'm just going to copy one atom. Okay, let's copy an iodine atom. Okay, if I can find an iodine atom, just a second. So let's say let's take this. So we've got so now we've got an iodine atom. Now you can clearly see that as you move away from the nucleus, the number of the size of the shell keeps on increasing. Like this outer one, that's a really big shell. So the maximum number of electrons that could be accommodated in it's got a lot of shells. It's got this one is shell number 1. This is shell number 2, shell number 3, shell number 4, and shell number 5. 5 would have a total of maximum of 50 electrons. Shell number 4 can have or accommodate a maximum of 32 electrons if that is shell number 3. Shell number 3 over here can have, I think in this case, it does have a maximum of, I mean, it's a complete shell. I think it's a complete shell. You can count shell number 3. So that is probably 18 electrons. Then you have 8 electrons in the second shell. And the first shell is the tiniest. It doesn't have a lot of space, so which is why it can just have a maximum of 2 electrons. So the basic idea is as you move further away from the nucleus, the number of electrons in the shells, they keep on increasing, and you can just follow 2n square. So you've got electrons in shells. Now in O levels, what you studied was you studied something called 288. In O levels, most of the time you just studied the electronic configuration of small atoms. Now in small atoms, the thing is you don't need so many shells. Like if it's the electronic configuration of fluorine, that's just 2 and 9. So small atoms, that's just 2 electrons in the first and 7 in the second one. You could have magnesium, that's just 12 electrons, so that's going to be 2 and 8 and 2. That's about it. So most atoms that you studied in O levels, they were kind of really small, and they didn't have a lot of electrons in them to start with. For example, the electronic configuration of iodine they never asked you about the electronic configuration of iodine. Anyway, so that's about shells, the protons and neutrons and the nucleus. How do you figure out how many protons, neutrons, and electrons are there in an atom? So you figure that out by just looking at the element, and you look at the elements. Let's say magnesium. That is, now the data booklet. Just a second. So we're going to look at the official data booklet. Now, in this, you have a periodic table, and if you look at the periodic table, you will have. So you'll have this one. Now look at magnesium over here. Magnesium in the periodic table is given as 12 and 24.3. So it's 12 and 24. Point 3. So remember previously when we were doing moles, I told you that this is the relative atomic. I mean, the bottom one is the relative atomic mass. Now, the relative atomic mass, I mean, an atom does not have 0.3 nucleons. 24.3 is the average mass of a magnesium atom. And its isotopes. So magnesium has a lot of isotopes. I mean, isotopes are a substance, we did study them. The only thing that is different is that they have different number of neutrons. So remember, an atom is defined by its number of protons and number of electrons. So the smaller number is the number of protons, and it's always equal to the number of electrons as well, as long as it's a neutral atom. For a neutral atom, the positive and the negative charge would be exactly the same. The neutron number can vary. For an atom, for every atom, there are multiple versions of the atom. I mean, the nucleus over here can have different number of neutrons. The nucleus or the neutrons, they don't do anything. So it doesn't really affect the properties of the element. So all elements are defined by the number of protons and electrons, especially by the number of protons. The neutron number can change. So if I just have a look at the isotopes of magnesium, so there would be all types of magnesium isotopes. For example, you've got, and the abundance is also given. I mean, we can just have a look. So you've got magnesium 26 as well. So it's got 2 extra neutrons. You've got magnesium 25 as well. That's got 1 extra neutron. So the abundance of the isotopes are also provided. And which is why when you calculate average, I told you that the number always comes out to be in decimals. Is this point clear?
Yes.
Okay, so, and is this clear? Aiza, Ahmed?
Yes.
Yes, sir.
So 24.3, remember there is no atom called 24.3. I mean, there is, because that's an average, that's the average mass of an atom. Either magnesium is going to be 24 or it's going to be 26 or it's going to be 25. It's always going to be, I mean, this is where it's written, it's 24, 25 or 26. So when you write the electronic configuration of an atom, be careful with the periodic table, because in the periodic table, average masses are given, so it's not the actual mass. So when you write the electronic configuration of, or you're asked about the number of protons, it has to be a very specific isotope. So it's either going to be 24. So if it's 24, then the number of protons is 12. The number of electrons is also 12, and the number of neutrons is the difference between the two, which is going to be 12 minus 24, which is also going to come out to be, it's going to come out to be 12. On the other hand, if you had magnesium, which is 26, then the number of protons are going to be exactly the same. The number of electrons would be exactly the same electronic configuration. Whereas the number of protons would be 14, neutrons would be 14 in this case. So a difference in the number of neutrons does not affect the properties of the element. So this is also very basic. You just need to know what a proton and how to calculate proton, neutrons, and electrons. But be very careful about the numbers given over here. Remember, there is no iron which has a mass of 55.8. It doesn't exist. There are different versions of iron. This is the average mass. So all these values, all these atomic masses, they're all average values because they include all the isotopes as well. So, I mean, you can't really find the number of neutrons by just subtracting 10.8 from 5. I mean, that's not how you're going to do that. It has to be a very specific boron. Either it's 10 or 11 or whatever it is. Similarly, if you even those that have like bromine, uh, even bromine is not a whole number. And the reality is that there is no bromine that's close to 80. There's bromine 79 and there is bromine 81 with different percentage abundance, which is why when you take out the average, it comes out to be right in the middle, which is 79.9. Actually, so that's one thing. Okay, so just be careful about isotopes, that you write the electronic configuration of a particular isotope. You don't use the relative atomic mass that's given in the periodic table. Is this point clear? Is this clear?
Yes, sir.
Achha, moving on. Now this diagram has some issues as well. That this diagram that you see on your screen, that's kind of an oversimplification because it looks like a planetary model like the solar system. It's like a nucleus at the center, which is positively charged, that's attracting all the electrons, and the electrons are spinning around it. So so this is not how an atom actually behaves. Or the electrons around an atom don't actually look like this. What they actually or more closely resemble is something like this. Let me just find a proper image. Just 1 second. I think I would have to. Probably I would have to draw this. So I'm just going to explain what's wrong with this particular image of an atom. And we can start off with a hydrogen atom. I'm going to describe how a hydrogen atom would look like. So the electron, and we can call it the wave particle duality, which I mean, you don't need to really go into a lot of detail about this. Just the basic idea, what is the electron wave particle duality? Or how do you describe an electron? Do you describe it as a particle or do you describe it as a wave? So this is what happens, that a hydrogen atom has one proton, and around that one proton, just 1 second. So here's a H atom, and we think of the H atom as there's going to be a nucleus which has one proton. That's a positive nucleus, and there's one electron that's around it. Okay, that's what we think the hydrogen atom looks like. But what actually happens is that the electron would kind of behave like a fly that's hovering around this suite. So there's this positive proton, the nucleus. Okay, let me put a circle on it as well. So that's our proton, positive proton sitting in the nucleus, and we've got a electron. Now this electron over here is not going to be stationary. It would be buzzing around the positive proton, or I mean the electron is very energetic, so it would be buzzing around like a fly that's hovering around a suite. So it would be attracted to the positive proton. The electron movement would be very haphazard. It would be attracted to it would be going in this direction, would try to leave it, but would be pulled back. So completely randomly, the electron would be going in all sorts of directions and would be buzzing around completely randomly. Is this idea clear?
Yes.
TK, is this clear to everyone? France, is this clear? Ahmed, Anna, Alicia?
Yes.
Acha. So the electron. So
Yes.
this model over here is kind of simplistic because it feels as if it's like a planetary solar system. It's more like a haphazard movement of the electron that is buzzing around the nucleus. It's attracted to the nucleus, which is why the electron is. If the electron becomes too energetic, the electron could escape. It could overcome the force of attraction and it could just leave. If it becomes very energetic, that's why atoms would lose electrons if you give them too much energy, because the electrons would become too energetic. If the electron is not energetic, it would just be buzzing around the nucleus. And it wouldn't be just a very slow buzzing. This would be happening. It would be just randomly moving in all sorts of direction, completely haphazardly, and would be all over the place. So you could think of if something moves very quickly, the only way, if something moves very, very quickly, I mean, you stop seeing it, right? And if something moves very quickly, an example could be a fan. Like if the fan is moving very quickly, what do you see? Do you see the blades of the fan when it's moving very quickly? Like if there are propellers on a plane, which has propellers, you can't see you can't see, what you only see is a blurred area where the propellers are. And the same thing happens for an electron, because the electron is moving very, very quickly. It is a subatomic particle, and it moves very quickly. So it would be just buzzing around really, really quickly around the positive nucleus, attracted to the positive nucleus. So when it does that, for a certain extent, just think of the propeller on a fan, the wings, the blades on the fan. They appear to be everywhere in that blurred area. So they're covering the entire blurred area, or they exist in the entire blurred area. So if a fan is moving, there's no place where you could place your hand in that area, because wherever you place it, the blades of the fan are going to hit you. Why? Because it appears to an outside observer that the blades are everywhere in that area. So you could think of the electron as occupying the entire space and being everywhere in that space. Is this idea clear? Is this clear?
Yes.
Okay. Nabila, is this clear? Aisha? Mariam, is this clear?
Yes.
And I'll show you, just for clarity, I'm just going to show you the image. So for example, just showing that if something moves very quickly, you stop seeing the blades eventually. Like if there's a propeller on a plane and the blades are moving very quickly, what you could think of is, like if somebody is going to ask you, tell me the exact position of the blades of the fan, you can't really tell. What you can say is that there's this spherical region around. I mean, the blades of the fan are somewhere moving in this area. I mean, you can't be very specific. And that is the same issue with the electron. You can't really tell where exactly they are. I mean, you know where they are. You know that they are somewhere in this area. But since they're moving very quickly, you can't really be very specific. So from now on, what would happen is, and let me clear this. So from now on, what would happen is that the electron electrons are not going to be are not going to be described by, like, you're not going to write an electron just like that the electron is over here, because you don't know where the electron is. What you know is the electron is hovering somewhere in a very specific area. So electrons from now on are going to be described by the region that they occupy, by the region or area that they occupy around the nucleus while they're hovering around the nucleus. This area is known as a high. It's known as a high electron density. I mean, high electron density means that it's the area where you're supposed to find the electron, or you can call it the high probability area. And that thing is known as an orbital. So is this point clear?
Yes, sir.
Okay, so we're going to step away from shells, and from now on, electrons would be described like, if we talk about an electron, we're going to talk about what space is it occupying around the nucleus. So where are you going to find that electron? So it's not going to be one specific location. It could be a specific area around the nucleus where you're going to have a high probability area, and you're going to have different types of orbitals. So there are going to be different types of regions where an electron could exist. So types of orbitals. The first type, number one, that's known as an s orbital, which we just did. So what's an s orbital? It's a spherical area around the nucleus, or spherical region around the nucleus. So for example, if there's a nucleus and there's a positive nucleus, and the electron occupies a spherical region around the nucleus. So the electron is somewhere in this particular area. So it's somewhere in this area. We're not sure where it is, but the electron is occupying the entire area around the nucleus. This is your high probability zone. And I can also show you what we mean by this. These orbitals have been pictured. So for example, so it's going to be something like this. I mean, for example, if you look at this, it's going to be this is the area where there's a high chance of finding the electron. So it's going to be a spherical region around the nucleus where you're going to find that particular electron. Just wanted to. I think that should be good enough. Couldn't find an actual image. So that's a spherical region. That's known as an s orbital. Is this clear? Is this clear? Anna, France?
Yes.
Now, there's
Yes, sir.
there's another type of orbital where another type of region where the electron could exist or could occupy, and that one is known as a p orbital. So you have a nucleus now, And this time the electron decides to occupy areas that are on either side of the nucleus, not everywhere around the nucleus. So the electron is kind of haphazardly moving around here or around in these parts. So somewhere over here, the electron is quickly or very quickly moving around. So it's whizzing over here or buzzing over here. So the electron is occupying places on either side of the nucleus. So the p orbital kind of looks like this. This is known as a double shaped. So the nucleus is at the center and the electron is attracted to it. So the electron occupies this area. It's a double shaped orbital with two lobes. Is this clear?
Yes.
And also remember that the p orbital has directions. Like you can turn it around. So here's your nucleus. The nucleus has axes around them. It's a three-dimensional the atom is three-dimensional, so there's going to be x, y, and z axis. And here's our z-axis. So think of this as three-dimensional. That's your x-axis, y-axis, and there's your z-axis. So all of them are 90 degrees to each other. Now this particular orbital can have directions. So it might exist on the x-axis, so the electron might occupy areas that are around or on the x-axis. So the electron would be buzzing somewhere in this area. That's known as a px orbital. So the region is called a px orbital. Then you've got the electron might occupy areas that are around on the y-axis. So one lobe over here, one lobe existing over here. So electron would be buzzing in these areas on the y-axis. That would be known as the py orbital. And the last one is the electron might be, the shape is going to be exactly the same except the electron is occupying regions on the z-axis. That would be called your pz orbital. So remember, it has directions. It could be on the x-axis, it could be on the y-axis, it could be on the z-axis. So there are three different types of p orbitals: px, py, and pz. Is this clear? Is this clear? Yes or no?
Yes.
So let's continue with this tomorrow then. Just make sure you revise this. Just remember that electrons, they exist in regions around the nucleus. So they could occupy a spherical area around the nucleus, or the electron could be whizzing in these double-shaped areas around the nucleus. So you're going to have three different types of p orbitals. So we'll continue with this tomorrow now. Okay, everyone, take care.
Okay, Allah Hafiz. Thank you.
Hafiz.